Math 3 Lesson Summary Video. Staking it. This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to locate points on concentric circles using the proportionality relationship. Veronica decides she will find the distance by setting up a proportion using degree measurements. Alice thinks they should find the distance by taking 1/16 of the circumference. Javier thinks they should use radian measurement in their calculation. So Veronica, Alice, and Javier are still trying to decide how to split up their archaeological site. They've decided 16 stakes may be better than 12 stakes. Again, it allows for more precision. But they're trying to decide how to actually physically measure that out. And they have 3 different strategies. Veronica wants to know what proportion of the circle it is by setting up with the degrees. So she wants to look at the degrees and say, well, I need to go this many degrees of the whole circle. So if I'm going 45 degrees out of 360 degrees, that's 1/8 of the circle. And so she's thinking of it as a proportion. Alice wants to actually figure out what the circumference of the circle is supposed to be, and then divide that number by 16, because that will actually tell her what distance does she need to walk on the circle before she puts a stake down. Javier thinks they should use radian measurement in their calculation. Since radian is already fractions, he doesn't even have to take the degrees and put them over 360 to figure out the fraction. The radian has already taken care of the fraction for him. So these are the 3 strategies that they're thinking about using. But Javier has a different idea. He suggests that they should figure out the locations of all the stakes in quadrant 1 first. And then it would be easy to find the location of the stakes in all the other quadrants by using those quadrant 1 locations. So this goes back to what we've been using over the past several days, that idea of symmetry. The circle is symmetrical. So if we can figure out where these are in the first quadrant, we can flip them over into the second quadrant and flip them down into the fourth quadrant and the third quadrant, and we can find everything using the symmetry. So we really only have to do the math for the first quadrant. He's already figured out some of the calculations. He did the calculations for the 10-foot circle, and they are wanting to do a 20, a 30, and a 40-foot circle. If we're thinking about proportionality, how could we use proportionality to our advantage to help us find the rest of these points without necessarily having to do a whole lot of trigonometry? So let's take a look at the information that he has. For each of these points, he does have the actual coordinates, and the S is actually the length along the arc. So what Alice was looking for, how far do I need to walk before I put a stake in the ground? And so we have that arc length, and the arc length is always from the beginning. So this arc length was 3.93, but the second one is this full length here. So it was 7.85. And then this one was 11.78 to go the whole distance. And this one was 15.71 to go the whole distance. What you may have noticed is that each one of these individual pieces is just 3.93. So to get the next one, we just had to say that times 2, or 3.93 times 3, 3.93 times 4. And so we're just adding the links together. We should be able to do the same thing once we figure out what one piece of each of the other rings is. To figure out what these points are, we want to use the fact that all circles are similar. All circles are proportional. So since these circles all have the same center, and we're moving out along lines that go through all of the circles, we're setting up a bunch of proportional pieces. So if this piece was 10 versus this piece being 20, those are corresponding sides to the similar shapes. And 10 to 20 is a scale factor of 2. it would make sense that all of the other pieces would also have to have a scale factor of 2. That's what similar proportionality means. So that means if this one had an arc length of 3.93, the next one should have an arc length of twice that, which would be 7.86. And then again, we just know that we are going around the circle in pieces that are 7.86. So 7.86 times 2 is going to be 15.72. Plus another 7.86 would give us 23.58. Plus another 7.86 would give us 31.44. So we're using that proportionality. We can also use proportionality for the actual points. If this is 9.24 in distance this way, this one should be twice that. So 9.24 times 2 is equal to 18.48. And 3.82 times 2 is 7.64. So since he's done all the work for our first circle, and we know that all of these circles are proportional. If this is 10 and this is 20, there's a scale factor of times 2. But if this one is 10 and this one is 30, this one must have a scale factor of times 3. If this circle is 40 and this one is 10, then this one must have a scale factor of times 4. So we can find all of those points to go along with the ones that Javier has found. Now this does still lend us one slight issue. Notice all of his computations are in decimals. And we have been working on trying to be more exact and using exact numbers and not just decimal approximations. So if we did want to figure out what these points were exactly, we would probably want to see if we could revisit those reference triangles. If we are thinking about 16ths of a circle, 360 degrees divided by 16 is equal to 22.5. So that's a decimal, and that's not really something I can work with without using decimals. But every other one, instead of being a 16th, is actually an 8th. And 360 divided by 8 is 45. So this second line, our second stake here, if we skip this one, is actually going to give us a 45, 45, 90 degree triangle. And if you recall, that is one of our special right triangles. So let's take a look at the 45, 45, 90 degree special right triangle. If you recall that if we know one side, one of the legs of the 45, 45, 90 triangle, the other leg has to be equal. It is isosceles. So that is very helpful because we know two of the sides are exactly equal. You can at that point use the Pythagorean theorem if you want to, or you can just remember that for those isosceles right triangles, the hypotenuse is always going to be times the square root of 2. So if this side happens to be 5, that would make this side 5, and this side 5 on the square root of 2. Now, it is a little more interesting if we happen to know the hypotenuse, like we do in these problems. In this problem, we know that the hypotenuse is the radius, and so it's 10. That first circle had a radius of 10. And so if 10 is equal to x times the square root of 2, and we want to know what these two sides are so we can write the coordinates of the point, I am going to have to actually divide both sides by the square root of 2. The problem that causes is that we can't leave a square root in the denominator. And if you recall, rationalizing a denominator, we just want to multiply the top and the bottom by the square root of 2. And when we do that, we get 10 square roots of 2 over 2. So dividing by the square root of 2 is actually the same thing as multiplying by the square root of 2 over 2. And so you can think of that in two ways. Both ways get you the same answer. This way has just already done the rationalizing for you. And we do get lucky here that 10 is divisible by 2. If you do 10 divided by 2, you actually get 5. So that means that our x and y coordinates for that first 45-degree angle, the coordinate points should be 5 square roots of 2, 5 square roots of 2. And so those coordinates are going to be the same. If you check that against Javier's answer, 5 times the square root of 2 is 7.07. And so that totally matches the numbers that he had. So this would give us an exact answer versus his decimal answer. The other thing we want to give a thought to is we've talked about the degrees, but we haven't really talked about the radians for these circles. If we go back to our angles here, when we were dividing it into 16ths, the whole circle is being divided into 16ths. If we use the strategy we talked about yesterday, thinking about fractions, counting by fractions, if the whole circle is 2 pi radians and we're splitting it into 16 equal pieces, then we're really just counting by 1/8 pi. So to find our radian measures, this would be pi over 8. This would be 2 pi over 8. This would be 3 pi over 8. And this would be 4 pi over 8. And those do reduce. 2 pi over 8 is going to reduce to pi over 4. 3 pi over 8 does not reduce. And 4 pi over 8 is pi over 2. But we figured that out yesterday. When we were counting by our fractions yesterday, we also got that 90 degrees was pi over 2. If we were to do the whole circle in those 45-degree angles, when we look here, we could start at 0. 45 degree, 3, 4, 5, 6, 7, 8 equal pieces. So 2 pi over 8 is 1/4 pi. So we have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. And that helps us to figure out our radian measures without having to do conversions, without having to memorize every single one of those numbers. All we're really memorizing is that to count the 45-degree angles around the circle, we're counting by 1/4 pi. So I can count by 45 degrees. 45, 90, plus another 45 would be 135, plus another 45 would be 180. So if we just think fractionally about the circle, we're always going to be able to find our degrees and our radians without having to do all of the conversions.